We're starting Unit 5, and in Unit 5 we're going to look at the properties of the slope estimator from the simple regression model, that little beta term. So the properties that we're interested in are the mean, or the expected value, and the variance, and also what type of distribution it is, which it turns out it's a normal distribution. Now, in order to analyze the properties, it's going to help if we spend a bit of time at the beginning just reviewing some of the algebra of summation signs. We're going to use summation signs a lot in this lecture, and I find sometimes it's a little hard for students to keep track of what you're allowed to do with them and what you're not allowed to do with them. So first little bit we'll just be reviewing some of the algebra, and then we move into the chapter material, looking at the properties of our least squares estimator, including a very important result called the Gauss-Markov Theorem, which is an interesting result that we'll be able to prove, which says our least squares estimator has the property of making the best use of the information in the data set. It gives us the most precise possible answer given the information that we have available in the data set. So it's an important topic this week, and get a nice sharp pencil ready, and here we go. First, let's talk about summations. So when I write this symbol, the capital Greek sigma, that means we're going to add a few things up. So if we say I equals 1 to 3 AI, if I write it like that, that's just A1 plus A2 plus A3. And so if ever you're looking at the summation sign in a formula and you're trying to get some intuition about what it means, it's really just a bunch of numbers added up. So now suppose that we have an expression like this, though. Let's say we have A over the sum of B. Now, I often won't bother writing the subscripts on the sigma, just because then it gets too messy. But if I have that, this can seem a little bit more awkward. You might not know how to think about that. So again, picture in your mind, it's a few numbers added up on top and some numbers added up on the bottom. And when you look at it like that, there's something you're allowed to do because it's a fraction. Well, there's one thing you're not allowed to do because it's a fraction. Let me back up a step there. You cannot do this. A1 over B1 plus A2 over B2 plus A3 over B3. You know, you can't do that. But what you can do is A1 over B1 plus B2 plus B3 plus A2 over B1 plus B2 plus B3 plus A3 over B1 plus B2 plus B3. This is okay. So I'll show you a simple example. Let's look at the example 2 plus 3 over 1 plus 9. Well, that is 5 over 10, and that's 1/2. Now, if I did this, 2 over 1 plus 3 over 9, that equals 2 plus 1/3, so that's 2 and 1/3. So you can see that's not the same thing. But if I do 2 over 1 plus 9 plus 3 over 1 plus 9, that is 2 over 10 plus 3 over 10, so that's 5 over 10, and that's 1/2. Okay, so when you have a summation sign on the bottom, you've got to think of that as one number, even though it's the group of them added up. But when you have the summation sign on top, you can think of those as the numbers in sequence. So, so this expression, as you can see, it's the same as this expression, which means this expression is the same as that. So just writing that out again. That is the same as A1 over the sum of the b's plus A2 over the sum of the b's plus AN over the sum of the b's. Now another thing we can do is factor out the term on the bottom. Okay, so, and what I mean by that is if we take 1 over the sum of these b terms and we multiply that by A1 plus A2 plus dot 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 plus AN. So that's okay. You can do that. You can factor this thing out. And again, just to go back to our numerical example here, if we have 2 plus 3 over 1 plus 9, that's the same as 1 over 1 plus 9 times 2 plus 3. Okay, so 1 over 10 times 2 plus 3, and that gives us 5 over 10, as we were hoping. So with this expression, you can factor something out by taking the bottom term off by itself, like we did here, and then leaving the top term in the summation form. Now, another thing that we should look at with summation signs is when you can take something outside the summation sign. So let's say we've got C times B subscript I. And C is a constant. And B is not a constant in the sense that we're adding up over the different values of I. So we've got C times B1 plus C times B2 plus dot 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 plus C times Bn. I'm just thinking about the light here. Hope that's visible for you. I can zoom in a little bit here. And just quickly try to fix focus there. There we go. Okay. So we've got C times B1 plus C times B2 plus so on and so on down to C times Bn. Well, we can factor the C out. So that's C B1 plus B2 plus Bn. And this term in brackets is our summation. So that's C times the sum of Bi. Okay, so when you have a constant inside the summation, you can take it out and put it on the left-hand side. Factor it out of the summation, like that. So any variable that's inside the summation over I that doesn't have an I subscript, you can take it outside of the summation. So let's do one more example here. The sum of say V times AI over the sum of W times BI. Well, that is, first of all, we can take the denominator off by itself. 1 over the sum of W times BI times the sum of V times AI. So that's a permitted step. And then we can take this w out here. So we've got 1 over w times the sum of bi. And we can take the v out of here. So that's v times the sum of ai. All right, did you see that? That's a constant, doesn't have an I subscript, so we can take it outside the summation. And then we can just move this v over here, so we have v over w, and we have the sum of ai over the sum of bi. All of these are equivalent, all of those are permitted steps, and there will be times when it's handy to be able to factor out terms from inside a summation. All right, so let's get started looking at the properties of the OLS estimator. All right, so let's think about our simple regression model. Y equals beta x plus epsilon. And we're leaving the constant term out, so we're keeping it as simple as possible. Now, we've talked before about what the least squares rule is. And the least squares rule is if you add up the squares of the error terms, and then you pick a value of beta that minimizes the sum of the squared error terms. And if you do that, well, it's a calculus problem. So we've seen before what the calculus problem is. But what we didn't do, we didn't look at what the solution is. Well, it turns out it's a formula. We get beta hat equals the sum of xi yi over the sum of xi squared. That's a little I there. Okay, so that's the formula for the least squares estimator. And we're not going to go through the derivation in this course. It's not too hard, but we're just not going to do it. But you can picture if you have a data set, let's say your y variable, these are house prices, and so you've got, if it's in thousands, let's say it's 277 and 429 and 316 and 812. And your x variable, these are the number of bedrooms in the house. So you got 2, you got 4, you got 3, and you got 4. So then if you drew those, if you did an XY scatter plot, and then you fitted a straight line through them, the formula would be, let's take the sum of, so it's x times y, so it'll be 2 times 277 plus 4 times 429 plus 3 times 316 plus 4 times 812. Oops. Now here's a mistake. I didn't need to write the summation because I've written out the individual terms and they're all added up. So I'm not adding these up and then adding up again. Just the one summation. And then on the bottom, we'll have the sum of these things all squared. So it's 2 squared plus 4 squared plus 3 squared plus 4 squared. Okay, so that would give us the slope of the line of best fit through these data points. Now you might be wondering, well, why this formula? Like, it doesn't look obvious why that should give you the line of best fit. Well, you'd have to work through the calculus to see why it comes out that way. But that's what the computer is doing. So the computer is going to apply that formula. Okay, now here's a little exercise for you to try. Let's write the formula out again. Beta hat equals the sum of x times y over the sum of the x's squared. Suppose suppose that all our values of x are the same. So we have x1 equals x2 equals xn, and they all equal 1. So we've got a column of observations on the y variable, and on the x variable, all we have is a column of 1s. What would that give us for beta hat? So I want you to just pause the video here and try to figure out what would the formula for beta hat be. All right, so I will show you the answer now, but I do encourage you to, first of all, try it on your own. So here's what the answer would be. We would have the sum of x times y. Well, that's just 1 times y, so that's just the sum of y. Okay, so the 1s just disappear. And on the bottom, we have the sum of 1 squared. Well, that's sum of y over, that's just the sum of 1. And so we're adding up 1 n times. So that gives us sum of y over n. Oh, well, that's just y bar. So if you regress a variable on a column of 1s, the least squares rule will give you the mean, which corresponds with what we saw earlier in the course when we showed that the mean, or the sum over n, is the least squares estimator of the center of a sample. Okay, so now let's look at this formula here. Beta hat equals x y over the sum of xi squared. And let's apply some of our summation rules just to break it apart a little bit. So we'll take out the denominator term, and now we have on the top we have x1 y1 plus x2 y2 plus xn yn. Okay, well, this is just a number. So even though there's a square term there, this just adds up to a number. And on this side, we've got the y's multiplied by the x's, but notice that there's no exponent on the y. So no exponent on the y. Therefore, beta hat is a linear function of the y's. In other words, beta hat is a weighted sum of the y variable, and the weights are constructed using the x's. Okay, so, and in particular, it's going to be x1 over the sum of xi squared times y1 plus x2 over the sum of xi squared times y2 plus xn over the sum of xi squared times yn. So we've got a number times y1 plus a number times y2 plus a number times all of the y terms. So it's a linear function of the y variables. It's a weighted sum, and the weights are constructed using the x's. Now this piece of paper, I'm going to put this aside, but keep track of whatever piece of paper you wrote that on. Keep track of where it is, because we're going to come back to it. We're going to need that again. All right. Now, because beta hat is a linear function of the y's, remember that the y's are normally distributed. So we saw that last time, that the y's have a normal distribution because the x's have a normal distribution. I can see some light is sneaking in on my desk here, and this is going to make it hard. So give me a moment, and I will close the blind here. So the y's are normally distributed, and the beta hat is a linear function of a normally distributed variable. So beta hat is a linear function of the y's. Therefore, beta hat is normally distributed, follows a normal distribution. Because a linear function of a normal variable is itself a normal variable. And so as long as we know the mean and the variance of beta hat, we can fully characterize its distribution. So we need the expected value of beta hat and the variance of beta hat to characterize how it's distributed, and then to construct confidence intervals. So before we figure out the expected value of beta hat, I'm going to show you a useful formula or a useful decomposition. So beta hat equals the sum of x times y over the sum of x squared. And y is x beta plus epsilon, right? So that's the regression model that we're using. So we're just taking y and replaced it with x beta plus epsilon, and we've got xi squared on the bottom. And then if I use all those rules of summation, then what I'm going to have up top here is the sum of, okay, so from that I have xi squared times beta over the sum of xi squared plus, and now I distribute the x onto the epsilon there, so that's the sum of x epsilon over the sum of x squared. And then this beta can come outside the summation. Remember, we're allowed to do that. And when I do that, I'm left with the sum of xi squared over the sum of xi squared. And they cancel out. So I'm just left with beta. So it's beta plus, now I can't do the same thing here because there's a subscript on the epsilon. So it's epsilon I times xi, and so I can't take it outside the summation sign, so I'll just leave it as is. Sum of xi times epsilon over the sum of xi squared. So this formula, we're going to call that, we're going to put a star beside it because that's a useful formula. We're going to use it a bunch of times as we analyze the properties of our estimator. Now, I should point out this is useful in theory, but it's not going to help us estimate beta because we don't know what beta is and we don't observe these error terms directly. So this is a valid decomposition, but it doesn't help us with estimation. All right, on to the first property of beta hat. And that property is the expected value of beta hat equals beta. And we're going to refer to this as the estimator is unbiased. So the estimator. So an unbiased estimator is one where its expected value equals the true value. All right, now, how do we know this? Well, let's go through the steps here. The expected value of beta hat equals the expected value of, now we're going to use that formula that we just derived, the one with the star. So it's beta plus the sum of x epsilon over the sum of x squared. Okay, now we're taking the expected value of the beta. We don't know what it is, but we do know it's a constant. So we can take it outside the expectation. So it's going to be beta plus the expected value of this sum of x times epsilon over the sum of x squared. Okay, now another thing we can do is factor out that term on the bottom. So we'll do this 1 over xi squared times the sum of x epsilon. Now, one of our assumptions, remember one of our classical assumptions, is that the x's are non-random. And when anything is non-random, it means its expected value just equals whatever you started with. So we can take this outside the expectation term. So because x is non-random, we can take it outside the expectation. So that means we're going to write beta equals 1 over the sum of xi squared times the expected value of the sum of x times epsilon. And again, we're using the assumption that x is non-random that we talked about last time. Oops, that should be a plus, not an equal sign there. And now we're going to do the same thing, but in this case, each of these individual x's, they're also non-random. So that means that we can take it outside the expectation as well. Or another way to think about it is we're going to take the expectation inside the summation, and then it's only applicable to the epsilon, because the epsilon is random, but the x is non-random. So what that looks like is the sum of x times the expectation of epsilon. All right, now if that step has you stumped, if you look at that and you can't see why I can do that, what I would suggest is just write it out a simple example like this: x1 epsilon 1 plus x2 epsilon 2 plus x3 epsilon 3. The expectation operator is linear, so we can write out the term separately: x2 epsilon 2 plus x3 epsilon 3. And now here you can see, well, if x1 is a non-random term, that's why we can take it outside. So that's x1 times the expected value of epsilon 1 plus x2 times the expected value of epsilon 2 plus x3 epsilon 3. And then that, you should be able to see why we can write that using the summation term. Okay, and then, so what have we got here? Well, we've got constant terms times the sum of x times the expected value of epsilon. But remember from last time, the property of epsilon, according to the classical assumption, is that this equals 0. So that equals 0, summation equals 0, this whole thing equals 0, so we're just left with beta. And we get the result. So the expected value of beta hat equals beta. This means that when we apply the least squares formula, and this is another version of the least squares formula, we're getting an unbiased estimator of the true slope, the true value of beta. We're not making a systematic error in our estimation here. Now, next up, we want to figure out the variance of beta hat. All right, so we'll write that just as V of beta hat, and again we're going to use that formula that we just worked out. So variance of beta plus the sum of x I epsilon I over the sum of xi squared, and it's a formula we just call star in the textbook. Let me look up what page it is. Here we are. It's on page 68. There it is. So that's the formula there. Page 68 in the textbook. Page 68. So variance of a constant plus something else. Well, the constant doesn't affect the variance. So then that is simply the variance of the sum of x epsilon over the sum of x squared. Okay, and now, as always, we're going to factor the bottom term out, and it's a constant, so we can bring it right outside the variance term. So it's 1 over the sum of xi squared. But remember, when you take a constant term outside the variance, you square it. Okay, so it's that whole thing squared. And we've seen this before. Remember, if we have the variance of y equals sigma squared, then the variance of a times y equals a squared times sigma squared. All right, so you've seen that already, and that's all we're doing here. Taking that out, and then that leaves us with the variance of the sum of x epsilon. Now we have the variance of the random term times this non-random term, and this is summed up. So it's going to be a similar type of step of taking out a constant term and then squaring it, and it's in the summation form, so it's going to be sum of xi squared times the variance of epsilon. Okay, so here, what I need you to do, if you look at these two lines and you think, oh, I didn't follow that step, what I would just suggest is you write out a simple example, and it can be something like variance of a1 epsilon 1 plus a2 epsilon 2, and if the variance of epsilon is sigma squared, what is the variance of that term? And you go back over the rules of working with variances, and you'll see, well, I'll just complete the thought here. So what you'll see is you get a1 squared times the variance of epsilon 1 plus a2 squared times the variance of epsilon 2. And so that means we've got the sum of ai squared times the variance of epsilon. So we started out with the variance of the sum of these terms, and then we get the sum of the constant squared times the variance of the term. So those steps are permitted. That's what we're doing. Okay, now we've isolated the variance of epsilon, and one of our assumptions is that this is a constant, that it's sigma squared. So that's one of the classical assumptions. Okay, so we have 1 over the sum of xi squared, all squared, times the sum of xi squared times sigma squared. And this expression here, although it might not be obvious at first glance, this is a number divided by the square of that number. So the top and the bottom cancel out, and we are left just with the number, in this case sum of xi squared on the bottom times sigma squared. Or we can just write sigma squared over the sum of xi squared. All right, so that's the variance of beta hat. Variance of beta hat then is the variance of the error term, sigma squared, divided by the sum of xi squared. All right, moving on. Now what we have is property 3 of the OLS estimator, of the least squares estimator, which is beta hat is distributed normally with an expected value of beta and a variance of sigma squared over the sum of x squared. So this property just ties the other properties together, but it says beta hat follows a normal distribution. And because we now have a distribution for beta hat, it means that we can do things like make confidence intervals and make probability statements. So let's say that we have beta hat distributed into 1, meaning mean of 2, variance of 1. And I should back up here, because this is all looking very theoretical and abstract, but when you get to doing regressions, which I guess you've already been doing, you'll know that you get the computer program gives you coefficient values and variances. And so these numbers drop out from the estimation. What we've done right now is in effect, we're figuring out what to do with those numbers. When we get them from the computer, what do we do with them? To answer that, we have to know what the distribution is, and to know what the distribution is, well, we have to make some assumptions. And so, so far, the classical assumptions allow us to say that our estimate follows a distribution that might be something like this. And so then, if the classical assumptions hold, it means that beta hat has a probability density function that might look something like that. So then we can ask, all right, what is the probability that beta hat is inside this region? So the probability that 1 is less than or equal to beta hat, which is less than or equal to 3. Well, we don't go through the steps, but you know how to do this sort of thing now. You turn this into a z-score, and then you use the z-tables, and you get the answer of 0.683. So this would be a good exercise for you to do to see if you can replicate that answer. And then the probability that 0 is less than or equal to beta hat, which is less than or equal to 1. So in other words, the probability that we're in this region here between 0 and 1, that is 0.136. Now, just to recap, what we've done is we've derived the distribution of beta hat. So beta hat is a random number because it's a function of normally distributed random numbers, so that makes it a normally distributed random number itself. So then we have this distribution, and with the distribution we can now draw bounds on where the optimal slope estimate is likely located. Now I want to back up a step and ask, are there other estimators? Okay, so you'll remember that the formula we're using is beta hat equals the sum of x, y over the sum of x squared. And we've derived some properties of that. Well, what if we tried a different estimator? Let's call it beta, and I'll put a tilde on top rather than a hat, and it will be y bar over x bar. Okay, so the average value of y divided by the average value of x. Well, that's an estimator. That's a slope estimator. We could ask, what are the properties of this slope estimator? So this one is the sum of y divided by n over the sum of x divided by n. So the n's actually cancel, so then it's the sum of the y's over the sum of the x's. So let's just see if beta hat is unbiased. All right, so beta tilde. Is beta tilde unbiased? All right, so our formula for beta tilde equals the sum of y over the sum of x. So then the expected value of beta tilde is the expected value of the sum of y over the sum of x. And we can take the sum of the x outside the expectation because it's a non-random term. So that's 1 over the sum of x times the expected value of the sum of, now y is x I beta plus epsilon. Okay, that's our simple regression models. That's what y is. And we can take beta outside the summation because it's a constant. So we have 1 over the sum of xi, expected value of beta times the sum of x. And we're taking the sum of both terms, so I'm just going to repeat the summation sign here. Okay, now this is non-random, so we can take it outside the expectation term altogether. So we're going to have beta times the sum of xi over the sum of xi plus 1 over the sum of xi times the sum of the expected value of epsilon. Okay, I think I did 2 steps at once there, but I'm just taking the expected value of the sum of epsilon, which is the same as the sum of the expected value of epsilon. And of course these go to 0. And here we've got sum of x divided by the sum of x. So those cancel, so we're left with beta. So this estimator is unbiased. All right, so if you had your data, if you had a data set, instead of calculating the least squares slope coefficient, which is that, you could calculate just the ratio of the sum of the y's to the sum of the x's, and that will give you an unbiased estimator of the slope. It turns out, though, that the variance of beta tilde, if we were to calculate it, and I'm not going to do that, but if we were to calculate it, the variance is greater than the variance of beta hat. Okay, so that means if we think of the distributions here, that's the PDF for beta hat. And that's the PDF for beta tilde. So the distribution is more spread out, and that means that we'll be less confident of our estimate. The variance is larger, the confidence intervals will be wider. It's got less precision. And another way to think about it is it's making less use of the information in the data set. The information in the data set consists of all the values of x and y, and if we're going to make the best possible use of that information, we want an estimator with the smallest possible variance. And in this case, the alternative formula gives us an unbiased estimator, but it's got a higher variance, so it's a less precise estimate. So we're making makes less efficient use of the information in the data set. I'll give you one more little example here. Let's do a third estimator. I'll call it beta, and I'll put a little 0 on top, just because I'm running out of symbols here, and we'll say max y minus min y divided by max x minus min x. Now, if you only have 2 data points, then this is actually the right formula to use. This is just the rise over the run, so you get the slope coefficient. But if you have a data set of the kind that we're working with, in effect, you're only taking 2 data points in the y's and 2 values of the x's, and so you're throwing out a lot of information. So it makes sense that this will be less efficient. It turns out this is also unbiased. I'm not going to go through the steps, but so that would also be an unbiased estimator. However, it's also going to be the case that the variance of this estimator is greater than the variance of the least squares estimator, beta hat. And this leads us to the fourth property. Out of all the linear unbiased estimators, the least squares estimator has the smallest variance. Okay, that's a very important result. It's a clever, very remarkable result, and this is called the Gauss-Markov Theorem. And Gauss-Markov Theorem, in a sense, what it does is it allows us to save a whole lot of time, in the sense we don't have to examine the properties of all the other estimators. We don't have to go through, because you could write down 1,000,000 formulas for estimators, some different ways of using the data in your data set. And if we didn't have the Gauss-Markov theorem, there's always going to be a chance that maybe there's something better than the least squares estimator. We should try all these other possibilities. Well, the Gauss-Markov theorem lets us off the hook from that. It says if the classical assumptions hold, you can't do better than the least squares estimator. That will make the most use of the information in your data set, and it'll give you an unbiased estimator with the smallest variance. Now, we are limiting ourselves in one sense. We are using linear functions of the data. Remember, I showed you before that beta hat is a linear function of the y's. So if we restrict ourselves to using linear functions of the y values, then Gauss-Markov tells us least squares is the most efficient estimator. It generates the smallest possible variance. So what I want to do is just, I'm going to sketch out how that works, okay, how the Gauss-Markov Theorem works. I'm not going to examine you on the proof, but I do want you to see it. So that will be what I do next, and then after that we're going to finish this section by looking at the final property, which is called maximum likelihood. All right, so let's go through the Gauss-Markov Theorem so that you know exactly what it gives us. So let's start off with the notion of unbiasedness, which we've said implies that the expected value of an estimator equals its true value. So that's a minimum requirement for an estimator. Now, to give you an example of a biased estimator, because sometimes it's not obvious if an estimator is biased or unbiased. Often it's not obvious. But let's take the example of, suppose we use sigma squared, and we defined it as 1 over n times the sum of the deviations of x around x bar. Okay, so that's kind of intuitively what you would think to do to measure the variance of something. You add up the squared deviations and then divide by n. The problem is that the expected value of sigma squared, sigma tilde squared, is not the true value. It's close to the true value, but it's not the true value. So it's a biased estimator. And so that's why we don't use that formula. In particular here we use 1 over n minus 1, and that corrects the bias. We always want to use an unbiased estimator. Now with the variance, we want it to be as low as possible. We want variance as low as possible. Okay. Well, we could get an estimator with a variance of 0. Suppose we use beta tilde equals 0. Okay, that's our estimator. No matter what the data set, we're always just going to say our estimate of the slope is 0. Well, then the variance of beta tilde equals 0. So that seems to be a good property. It's got no variance, a very precise estimator. The problem is it's biased. Okay, but so the expected value of beta tilde does not equal beta, except by fluke. But in most cases, that's not going to be true. So it's biased. Okay, so we're going to limit ourselves and say, well, we only want to use unbiased estimators. And then within that category, we want to get an estimator with the lowest possible variance. And then we want linearity. Okay, and the reason for this is we want to be able to say something about the distribution of the estimator. And the underlying randomness in our regression model, we're assuming is normal. And as long as we stick with a linear function of normal random variables, then we get a normal variable as an output. So that means that what we want to do is we'll use an estimator. And if it's a linear estimator, then we can write it as a linear function of the y values. And since the y value is normally distributed, that means beta is normally distributed. So this allows us to characterize the probability distribution. Okay, so if this is a nonlinear function of the y's, it then gets a lot more difficult to characterize a probability distribution. Sometimes it's still possible. It's just extremely difficult. Now, I should also point out here, the OLS formula, each of these CI terms is xi over the sum of xi squared. And that's in the case of our simple regression model. All right, so we've seen that previously. This is xi over the sum of xi squared. Okay, so the form that we're going to use for our estimator then is the linear function. So let's take the expected value. So expected value of that linear estimator, so that's the expected value of C1 y1 plus C2 y2 plus ... plus Cn yn. I'm doing this because I'm going to want to check and figure out what needs to be true for this to be an unbiased estimator. Okay, and the C terms are constant, so it's C times the expected value of y1 plus C2 times the expected value of y2 plus Cn times the expected value of yn. Okay, and now each of these y's is C1 times the expected value of x1 beta plus epsilon 1 plus so on, Cn times the expected value of xn times beta plus epsilon n. All right, so we just plugged in the definition of our simple regression model there. And now you should be able to do this sort of at a glance. You know, you take the expected value. Well, this is a constant. This is non-random, so they're going to just come outside the expectation. And then you've got the expected value of epsilon, and that's 0. So we're going to be left with C1 times x1 beta plus all the way down to Cn xn beta. Okay, and now we're going to turn this into a summation. Beta is a constant, so it'll be outside the summation sign, and inside the summation sign we will have Ci times Xi. Okay, so if this is going to be an unbiased estimator, then unbiasedness requires, all right, can you see the condition that it's going to require? We want the expected value of beta hat L to equal beta, so that's going to mean that the sum of Ci Xi must equal 1. All right, so that'll be a condition that for a linear estimator that gives us unbiasedness. Now we also want to know what the variance of this estimator is going to be. So that's going to be the variance of C1 y1 plus all the way through to Cn yn. And we can just go through the various steps that we've seen before, and we get C1 squared times sigma squared plus up to Cn squared times sigma squared. And then putting that in summation notation, we get sigma squared times the sum of the Ci squared terms. Okay, so what is best linear unbiased estimator, or BLUE as it's called. And by best we mean smallest variance. Well, to answer that question, to get the answer to that question, we need to solve a calculus problem. Solve a calculus problem, and in particular it's a constrained optimization. What we want to do is minimize the variance of our linear estimator by the choice of the CIs. So we're going to choose the CIs to minimize that variance, subject to the sum of CI xi equals 1. All right, now, if you've done math econ, you'll have seen Lagrange multipliers and constrained optimization. The Lagrange function is sigma squared times the sum of CI squared minus lambda times the sum of CI xi minus 1. Okay, and then what you want to do is take the derivative of the Lagrange function with respect to CI, and so that is 2 times sigma squared CI minus lambda xi equals 0, I equals 1 to n. And so that gives us, we rearrange that to get C equals lambda xi over 2 sigma squared. And we also have the condition that the sum of CI xi equals 1. And I don't need to go through the rest of the derivation. It is in the appendix to the chapter. But if we combine these, we get CI equals xi over the sum of xi squared. Okay, now, I think a long time ago I told you to set a piece of paper aside. I said we're going to come back to that. You're going to need that. And the piece of paper had this on it. So we beta hat, and we just expand the term out, and we get beta hat equals this linear function of the y's. And you'll notice that this is C1, and this is C2, and this is Cn. So that's the form that we got by solving this constrained optimization problem. So, in other words, the least squares formula is BLUE. Among all the linear unbiased slope estimators, the least squares estimator has the minimum variance. And we can interpret that to mean it makes the best use of the information in the sample. Okay, so that's how it's solved. What you need to know is, under the classical assumptions, the OLS estimator, the ordinary least squares estimator, OLS estimator, satisfies the conditions for the Gauss-Markov theorem. Under the classical assumptions, the OLS estimator satisfies the conditions for the Gauss-Markov theorem. By satisfying the conditions for the Gauss-Markov theorem, that means it yields the best linear, unbiased estimator. There's no other slope estimator that will give us a lower variance. So that is the fourth property of the least squares estimator, and then we just have one more property to discuss. Okay, so we're now on to the last property of the estimators, the property 5, and this one goes by the name maximum likelihood. Okay, and at the beginning I mentioned the idea that you pick an estimator according to a rule. So we've been focusing on the least squares rule. Least squares rule. And the least squares rule is pick beta to minimize something. Do you remember what? To minimize the sum of the squared errors. Sum of the squared errors, or the residuals in the case of the regression model. So it's a solution to a calculus problem, minimize the sum of these squared terms. Now we're going to look at a different rule. We're going to call it the maximum likelihood rule. And that will be pick beta to maximize the likelihood that you identified the right distribution. So let's do this through an example. So I'm going to have a data set that has just 5 observations in it. 1, 2, 3, 4, 5. So my observations are 4, 7, 6, 4, and 5. Okay. I'm just going to so I have the numbers here that run from 0. Let's run the numbers up to, say, 15. And so this will be 5. That'll be 10. Here's what we're going to do. We're going to try to guess. Let's suppose we knew these were normally distributed random numbers. So we're going to say that x is distributed normally with a mean of mu and a variance of sigma squared. And what we need to do is guess which values of mu and sigma squared would give us a distribution that if we took 5 draws from that distribution, we might get numbers like this. So you can pick any values of mu and sigma squared that you like. So let's start with mu equals 10 and sigma squared equals 2. Well, that is going to be a distribution that looks something like this. And now our sample is, so we've got 4, and we've got 7, and we've got 6, and we got another 4, and we have a 5. Okay, so this is where our sample is. And that sample is out in the tails of this distribution. So if you think of the likelihood of pulling these kinds of numbers out, they're not very likely from a distribution like that. So if you have a distribution, a normal distribution with a mean of 10, a variance of 2, the likelihood of drawing a 4 is very low. And 7, well, it's still low. 6, it's still low. 4, very low. 5, very low. Okay, and if I had to come up with an actual measure of, like to quantify what I mean by low, we could use the height of the density function. So the height of the density function here is a measure of the likelihood. It's what we're going to use as our measure of likelihood. Well, now let me pick a different distribution. Let's say mu equals 4 and sigma squared equals 2. All right, well, that's mu equals 10. So now we're going to have our distribution centered here. All right, well, now it's going to be, if we're going to use the height of the density function, well, this is much better. It's very high. 7, well, that's medium. 6, pretty high. And then these two are very high, close to the peak. So what I've done here is I've started with an assumption, okay, I know these are normally distributed, but I don't know the mean and the variance. So if I try this mean, then it means that my sample is mostly out here on the tails, which is unlikely. If I start with this mean, then my sample is closer to the middle. Some of the values here are right in the middle, and some are out on the tail, so that's more likely. So what I'd like to do now is there a rule I could follow to pick the mean and the variance that would make it the most likely that I could have drawn that sample? And that's what maximum likelihood estimation does. Now, to do maximum likelihood estimation, what we need to do is, so I've already kind of hinted at it, but what we're going to do is we're going to say the likelihood of any one observation in the sample is the height of the density function at that point. So then that gives us a likelihood value associated with every point in the sample, and then we're going to add them up. All right, so how do you get the height of the density function? Well, the formula for the normal probability density function is if x is the draw, so it's the realization, it's the number that we've drawn. The likelihood L of x is 1 over square root of 2 pi sigma squared times exp minus 1 over 2 sigma squared x minus mu squared. All right. And exp, just in case you're wondering, exp of a variable. That's e to the power of y. And e is that number you would have encountered in calculus. It's the inverse of the natural log function. All right, so this is the formula for the normal probability distribution when you have that bell-shaped curve and you have a variable x. This formula is gives you that shape. Now, I remember when I first saw this formula in an econometrics course, and I just thought this is the most incredible formula I've ever seen. It's just an amazing thing, and here's why. Because when you think about the most confusing, unstructured stuff that goes on in the world, that's randomness. And randomness, or we call it noise, it's just all the stuff that seems unexplainable. So it's the pattern of rainfall on a roof. It's the behavior of animals in the wild. It's the behavior of large crowds of people, particles in motion. It's everything that seems random, unexplainable, and unpredictable. And yet, it has structure to it. In fact, it's got a structure that we can write down mathematically. In virtually every case, random processes converge on a normal distribution. And so this distribution, this formula, like I know when back in the olden days when people were on campus and you go to those poster sales, and sometimes people like to buy the poster of Einstein with E equals mc squared because it's kind of a cool formula. But I think if you're going to get a poster made of a formula, you should put the Gaussian formula for the normal distribution up, because this one is just amazing. I mean, this really, it makes sense of all these random processes in the world, and it says somehow, for some reason, all this noise and chaos and randomness actually has structure to it, and it converges into this profile. And another thing I find wild is pi. What is pi doing there? Like I don't know how this is derived. It's one of those things I keep meaning to look it up, but it's derived as the limiting distribution of another distribution called the Bernoulli distribution, which is very simple binary random numbers, heads or tails, coin toss type things. And but pi is, if you remember your geometry, it is the ratio of the diameter to the circumference of a circle. What on earth is it doing in the middle of the bell curve distribution, the formula that defines the structure of randomness in the world? That's one of those just amazing things that happens in math, when things that look like they should have nothing whatsoever to do with each other, and then they end up stuck together like this. All right, so sorry, I got a little diverted there, but this is that amazing formula for the normal random distribution, and it's like it describes the structure behind so many things that seem inexplainable in the world. Okay, so this is the likelihood function. So if you have a value of mu, if you have mu and sigma squared, you plug a value of x in, and it tells you this number here, the height of the distribution. Okay, so then if we have a whole sample of numbers, as in our example, then we can calculate the likelihood of each one. So 4, 7, 6, 4, 5. And so if we have mu equals 10 and sigma squared equals 2, then we can calculate the likelihood value by plugging
x in, and so in this case it's 0.000035, very small number, 0.0297. I had a computer do these, 0183, 0.000035, and this one is 0.0019. If I use mu equals 4 and sigma squared equals 2, then the likelihood values are much higher. So 0.282, 0.0297, 0.1037, 0.282, and 0.2196. All right, so, and how did I get these? So I use this formula. I take mu equal to 4, sigma squared equal to 2, and I just plug in the x's, and I get Lx for each one. So these are bigger numbers. So this is more likely. This is more likely to be the right answer. The maximum likelihood here, you might think, well, okay, we'll take the combination by taking the average of all of them. That's close. We're actually going to multiply them all together. We're going to take the product of all of them. So to figure out the likelihood of the sample, rather than use the average likelihood value of each point in the sample, we're going to use the product of the likelihoods. So we maximize product of likelihoods. So remember that Lxi equals 1 over 2 pi sigma squared exp, and I will never ask you on an exam to write out this formula, but I would suggest that you memorize it anyway because it just makes you a good person. Now that's the likelihood for an individual observation in the sample. I put a little subscript there on xi. We will call the likelihood function for the whole sample, given mu and sigma squared. It is the product of the individual likelihood values. This capital pi, that means product. So it's, if we were going to add them up, that would be a giant sigma, but the capital pi means it's the product. It's one times the other. Okay. So now our problem is choose mu and sigma squared to maximize L. And here we're not going to go through the steps of the derivation. I will say that the way we make this easier is we take the log of the likelihood function, because then all we're doing at that point is adding up the log of each of the individual likelihoods. Because remember, if you have a bunch of numbers or a bunch of variables multiplied together, you take the log of the product, that equals the sum of the individual logs. So the solution is the solution ends up being the minimum of xi minus mu squared. Now, why is that? Well, it comes from this term in here. So when you take the log of this expression, then you've got this term on its own, and we're adding up the log of that term, and since there's a negative here, if we want to maximize the sum of the log values, that turns out to be the same as minimizing the sum of these values. And so we're minimizing the sum of the squared deviations. So minimum of, so in other words, to maximize L, minimize the sum of the squared error terms. So that gives us the maximum likelihood value of mu. However, the variance is a little different. So the maximum likelihood estimate of sigma squared, that's the sum of the error terms divided by n. All right, and that's different from the least squares estimator, where it would be n minus 1. And so the maximum likelihood estimator of sigma squared turns out to be a little biased. Not a lot, but a little bit biased. I'll just rewrite these out in the familiar notation of our regression model. All right, so we have y equals x beta plus epsilon. Now we have to start with a distribution assumption here. So we have to assume that the error terms follow the normal distribution, because it's that assumption that tells us what the form of the likelihood function is, in particular the normal probability distribution. So then the likelihood function, given our data and our estimate of beta and sigma squared, it's going to be the product 1 over root 2 pi sigma squared exp minus 1 over 2 sigma squared yi minus xi beta squared. Okay, so that's epsilon. I don't need to subtract the mean of epsilon because it's 0. So so the expected value of epsilon is 0. So we don't need to subtract its mean. So we just have y minus xi beta squared. So this is a function, and we're going to pick the value of beta that maximizes that function. And if you do that, maximize L with respect to beta, then that gives us beta hat maximum likelihood equals the sum of x, y over the sum of x squared. Okay, which equals beta hat OLS. So the OLS estimator is also the maximum likelihood estimator. And sigma hat squared, maximum likelihood, is the sum of the error terms over n, and which is not the same as sigma hat squared OLS. So if it was OLS, that would be n minus 1. So a little bit different, but the slope coefficient is the same. And so that's why we have the property that the least squares estimator is also the maximum likelihood estimator. All right. Well, we've covered quite a lot of stuff in this lecture. This was a bit of a dense one, as I warned you. So let's just go back over the section here and see what we've done. So we're looking at the properties of the ordinary least squares estimator. And turn the light on here. See if that, adding more light doesn't necessarily brighten the image. Do it this way. Might be a bit better. Okay, so that's our estimator, the least squares estimator. I'm looking at page 67 in the textbook here. And then we want to know what are the properties of the estimators. So the expected value is the true value, so it's unbiased. That's the first property. The variance is given by this expression here. Try to sharpen that up a little bit. There. It's given by that expression, sigma squared over the sum of x squared. The third property is that the distribution is normal, and with the expected value of beta and the variance of sigma squared over xi squared. And that follows from the assumption that the error terms have a normal distribution. The fourth property is the Gauss-Markov Theorem. And that means that our least squares estimator makes the most efficient use of the data information. So it's blue, best linear unbiased estimator. And the fifth property is the maximum likelihood estimator, beta, is the OLS estimator. As long as the classical assumptions hold, and one of those classical assumptions is that the error terms follow a normal distribution. Okay, so that gets us to the end of section 3.4, and we're kind of over the hill in terms of some of the theory, and we start on 3.5 next week. See you then.